In this lesson, we're gonna focus on memory management in C++, and that would get us to finally work with dynamic constructors and something called destructors. Finally, we're gonna discuss how to avoid leaking memory in C++. Here in VS Code, I have the program that we worked on in lesson 3, the one where we had the students and the university. So here we construct the 3 students, we update some of their grades, we create the university, we add all of the students to the university, and we print all student records to the console. So let's compile and run this. And we see that all the records have been printed and that the grade for the second student has been updated to 96 as per this line here. Now, it wasn't random that in lesson 3, I placed the 2 calls to the setGrade method right here before adding the students to the university. So let's take a look what would happen if we did things the other way around. So I'm going to cut the method calls from here, and I'll place them down here. And we'll save this and recompile it. And now we see that the grade for the second student is still 80, as if this line didn't happen. So that sort of sucks. And why is that? Well, it has to do with the way vectors work in C++. And the way vectors work in C++ is that they work on copies of the data that they're given. So once we call the addStudent method, the student is given to the pushBack method to get pushed into the vector. And that method just makes a copy of whatever the student is at that point in time. And then that copy lives in the vector completely disconnected from everything else that's going on. So once we update the grade, sure, we update it on S2 here, but the copy that's in the vector is long gone and is disconnected from anything that's happening here. So one strategy we could try is we could try to pass the student in by reference. So we can just add an ampersand here. And VS Code complains right away because now we have a mismatch with our header. And C++ is sort of annoying this way that you always have to fix the header. So we save this, and then this is all good now. So we save this here, and we'll recompile. Let me actually clear this, and we'll recompile. And unfortunately, we're still stuck. And this is sort of weird, but the way vectors work is that even if you give them a reference, they're just gonna essentially say, well, we have access to the full object, and we're just still gonna make a copy of it. So the way to do things here is to use pointers, because then you just copy the memory address into the vector, and then each time you go into that vector, you would have to follow the memory address into memory. And in memory, you can modify things as you wish. So like pictorially, if we were doing things either by a value or by reference, we would be making copies of S1, S2, and S3 into the vector. Now, on the other hand, if we had a vector of pointers, then we would just store the pointers in the vector. And those pointers will be pointing to somewhere in memory wherever the students are. So if we make changes to the students right here, well, as far as the vector is concerned, it just has the pointer. So when you want to access it, you're just going to follow the pointer into memory. And find out whatever is there. So let's try to implement this. So we'll make this a vector of pointers, and then we'll change this to a pointer. And then let's see, so we'll start making changes in the header. So we'll change this to a pointer. We'll change this to a pointer. We'll save the header. And we're fine here. This here is complaining because of the dot. So we have to change this to an error. So we are so far so good. Now we have a problem here because those are just students. We need student pointers. So let's declare and initialize pointers to students. Like that. And then we're going to change all of this to the pointers. And then that should be okay. We'll save this. We'll compile. And now we see that the grade has been updated to 96. And we are all okay. So the next issue is, what if we can't have everything in main? Like, what if this program grows large enough that we would want to start extracting some of this code into helpers? So let's do this here now. So I'll make a helper here. I'll call it build university. And I won't have it take any arguments, but I will, of course, have it return a university. And now I'm just going to cut everything that we have here into this helper. And I'll have it return this U that we declared and built here. And then here we'll have a university that's just going to be the result of this helper. And then we'll try to print the records on this university that's coming from this helper. Okay, so let's save this. And then let's compile. And so far so good. And let's try to run this. And things didn't work out. So it looked like it started printing the record, and then, well, that ID and the grade definitely didn't look good. Definitely not what we expected. And then on the next record, we just crashed. So, well, this goes back to the whole idea of not returning, or storing for that matter, pointers to local variables. Because what happened here is that we build those students, we initialize pointers to them, and then we store the pointers into this vector. And then by the time we got down here to print the records from the vector, this function was long gone, and all of those local variables have been deleted. So, and the memory has been allocated for something else. So we were just shooting at random memory addresses when we tried to print the records. And what happened here is that on the first try, we went into some memory address that was at least looking somewhat legally. And we just printed garbage values. But by the time we got to the second record, we were shooting into memory addresses that were in a very protected space. So these operating system's protection kicked in, and it says that this program is doing wild things and I have to crash it. That's what a seg fault means, is that you really access some very illegal memory. And for security, the operating system has to kill you. As a quick aside, that's what happens on a blue screen of death, is that the operating system itself seg faults. Like on a blue screen of death or on some big crash, essentially the operating system itself seg faults and it has to quit and restart the computer. But here it just kills the program. Okay, so we really want to get around this whole deal of returning or storing pointers to local variables, because it clearly doesn't work here. So, and this is where the whole concept of dynamic memory and dynamic constructors and memory management in C++ comes in. So for any given program, this is what the general layout of its memory space is going to look like. So any program that's running out there is going to be given its own version of this in the computer's RAM. And we start out here with the program's code. So this is literally like the code that we have written. It has to be stored in memory somewhere. Then we have the global variables, and we haven't worked with the global variables in this video series, so you don't need to be too concerned about this. And then we have the stack, and the stack is where the local variables get stored. And they're stored on the stack in chronological order. So as your function builds up, it puts the variables onto the stack. And as the functions execute, they sort of move up and down the stack. So you might put more variables on, and then your function returns, and you might kill some of those variables off, and so on and so forth. So this is really a linear and chronological space. Then you have the heap. And this is general purpose memory that you could ask to be reserved for your variable. So what you do is you make a call to reserve some space on the heap for some variable. And the program says, okay, cool, here's your space. And it returns you a pointer back to that space. So pointer P1, and then you use that memory. And then next time you ask it, it will go into a completely different random space, and it will return you a new pointer P2. And that memory is really reserved for you until you say that you're done with it. If you don't say that you're done with it, that memory is still going to be assigned to your variable. So if you are going to use the heap, you're not going to get into this issue with a stack where things move back and forth, and as functions return, your variables just get knocked off. If you put your variables onto the heap, then they're just going to live there until you're done with them, and you're going to be fine. And getting memory from the heap, making your request, is where the new keyword comes in. So whenever you use the new keyword, you're asking to get a spot in memory on a heap. So I just, before we do get to use the new keyword, I just wanted to illustrate the point about the stack. So I'll put a few print statements here that are just going to print the values of those pointers. So I'll say value of P1, and I'll put P1 here. And then we'll do the same thing for P2 and P3. And let's just quickly save and run this. And okay, this part still crashes, which is fine because it crashed before. But what I really wanted to show you is that the location of those pointers, or the locations of students S1 through S3, is really linear and chronological on the stack, because we can see that all of those addresses are one after each other. And what they differ by is they differ by the size of each student. So if you subtract this stuff here in hex, so this looks like the difference here is 30 in hex. So this looks like, if I'm not mistaken, 48 bytes. So this is how big each of the students is, and that's the difference in the memory addresses between them. So if you go back to the diagram, that's what I mean by things sort of going here in a chronological order on the stack, is you have something like that student where the address ended in 00 here, and then you have the next one that is 30 here, and so on and so forth. Okay, so that was just for illustrative purposes. But now let's finally fix this mess of the pointers here. So the way we're going to do this is we're going to turn the constructors that we're using here from static into dynamic ones. And we do this the same way that we have done in Java. We just put the new keyword, and then we make the call to the constructor. So as you can see that this line here is exactly what you would typically do in Java. And now this thing here is complaining, and it's complaining that we can't convert from student to a student pointer. And that's because the students here now need to be pointers. As I said, that whenever you're asking for memory to come back from the heap, like I illustrated here, it returns a pointer. So as soon as we are putting the new keyword here and we are making a call to this dynamic constructor now, you have to return a pointer. And then we can really get rid of all of this stuff here because we don't need those artificial pointers anymore. And then those don't exist, but we can change those to all the S's. And then this here is an issue because we are not using the error. Okay, so I think we are okay. So let's recompile this. And look at that. Now we don't crash, and the grade is updated to 96, and everything is fine. And that's because we finally put those students up on the heap, and that's what happened here. Despite that everything works, we still do have a problem. As I mentioned, once you reserve some space on the heap for your variable, that space would stay reserved for as long as you need it. However, at this point, we haven't really discussed how to tell the heap that we no longer need the space. So what we actually have here is something called a memory leak. So what this means is that we keep allocating space from the heap, but we aren't really telling the heap which space we no longer need and which space could be reused for something else. So you can imagine if this goes on for long enough, you would eventually run out of memory. There is a professional way to tell if your program has a memory leak, and it's this tool called valgrind that you run from the command line. And you give it the name of the program as argument. And then here it tells us that we definitely do have a leak, and we're losing 120 bytes and 3 blocks. And hint, hint, the 3 blocks are the 3 students that we have up here. If your memory leak is really wild, you can even see it on a tool like Task Manager. You can see the memory climb. And then once you kill the program, there is a sharp drop-off. But of course, for all the finer details, you just have to use valgrind, and valgrind is usually very precise. Okay, so enough said. How do we deal with it? Well, what we use is we use the delete keyword to undo every new keyword, and then we use destructors to undo constructors. So then, of course, in Java, we didn't have the delete keyword. We didn't have a destructor because their garbage collection did all of this for us automatically. Okay, so let's go to our program and let's write ourselves a destructor and clean things up here. So we'll go to the header first, and we'll declare the destructor. And the name for the destructor is the same as for the constructor. You just put a tilde at the front. So I think as far as the header is concerned, we are good to go. So now we'll go up here to implement the destructor. So you, of course, need the name of the class followed by the scope resolution operator. And then in the body, what we want to do is we want to get rid of all of the students that were created somewhere. So I will just copy this for loop. And we are not going to print records here. What we want to do is we want to delete all of those students. So this here is going to iterate through the vector, and it's just going to call the delete on each student pointer that it comes across. And delete you have to give the delete a pointer so that it can follow that to the heap and clean it up there. Just like new returns a pointer, you give the delete a pointer. Okay, so let's save this, and we'll clear the console, recompile, and run to make sure everything still works, and that's fine. And then we'll now valgrind this. And we see now that the heap is totally free and that no leaks are possible. That's great. That's what we wanted to have. So the general rule of thumb is that you want to have the number of delete keywords match up with the number of new keywords. And the reason why memory leaks exist is that it's typically quite hard to figure out how to match those things up. Because like in this case, for example, we have one function that's just using new keywords on their own individually to create things. And then the destructor, it just has a one delete keyword, but of course that's in a loop. So you would expect that the number of delete keywords here does match up with a number of new keywords. And then the destructor for university, it gets called when this university goes out of scope. So that's why when this U went out of scope, the memory was cleaned up, and everything was fine. So what I would like to finish off with here is I would like to fix this mess that we had back in the pointer lesson, where we had the function foo that declared and initialized an integer x and then returned a pointer to that integer. And then we tried to dereference the pointer back in main, and bad things happened. So back in main, you get a garbage value when you try to dereference the pointer. And the way you fix this is just like we done with the university program, is that you just put a new keyword here, and then you formally call the int constructor. And of course this complains right away because this needs to now be a pointer. And then we don't really need this line here because we can just return x, and we can save this and recompile it. And we see that now the value that's printed in main is what we want. Of course, here, if we were to valgrind this, we do get a leak of 4 bytes, and 4 bytes is exactly the size of the integer that we are not deleting. So to fix this, we would just write delete and then give it the pointer that we want to clear. And so compile, run, valgrind, and now there are no leaks. Great. Just something else to mention is that doing something like this is also pretty bad, because in the worst case you might start deallocating memory that already been deallocated and allocated for something else. So this is typically called the double free error, and is also something to watch out for. So I'll just actually comment this out. Okay, so to summarize, so in this video, we talked about the general memory layout. And we talked about how stack stores local variables to which you shouldn't return pointers or store pointers to. Variables there are stored statically in chronological order that's determined at compile time. And then the heap is really your general purpose memory that you can allocate dynamically on request at runtime. And you do that using the new keyword. So then we discussed how a delete undoes the new keyword and how a destructor undoes a constructor. And that in general, you want to have the number of new keywords match up the number of delete keywords. In this video, we finally worked with a dynamic constructor with which you're familiar from Java. You just don't need the pointer in Java, of course. Before that, we worked with the static constructors. And then here's the notation for the destructor. And we talked about how to use Valgrind to check for memory leaks. And then finally, here is sort of the formal terms for all of the memory issues that we discussed thus far. So those seg faults that we had where we were trying to use pointers that were no longer in scope, the proper term for those is typically a dangling pointer. So that sort of makes sense. And then, of course, there were the memory leaks that we talked about, and I briefly mentioned double free errors that happen when you're trying to delete the same pointer twice, or you're just trying to delete a pointer that has never been allocated. Okay, thank you.